and welcome again in this advanced conduction series. So firstly, let us briefly recall that what we have done in our previous lecture. So we were in a very interesting stage, and we were discussing about the basics of the tensor algebra as well as the basic rules of dealing with indicial notations, right? So I almost completed all the rules of indicial notations, and therefore I will be today, with the help of them, I will be deriving the fact that for an isotropic material only, the thermal conductivity tensor boils down to a constant multiplied by an identity matrix. Okay, so let us directly dive into that. So just let me put today's lecture number, that is, it is lecture 6, right? So lecture 6. So just let me briefly do the recapitulation here, that we ended with this question, that can we find a mathematical correlation between this AI and AI dash, right? Or between this AI and AJ dash, anything, okay. I mean, yes, this is technically more correct, AI and AI dash, it is technically more correct, but I thought again that it could have been written also AJ dash, because nowhere it is written that you have to find a correlation between only AI and AI dash. You can have a correlation between AI and A2 dash also, okay. But we know that in two sides of an equation, that is in RHS and LHS, we cannot have different free indices, that we know, okay. So our derivation, I mean any equation should obey this fact, okay. So we should just keep in mind this fact, that in any term in a particular equation, we cannot have different free indices, okay. So let us try to do this thing, that is to derive a mathematical expression or a mathematical relation between AI and AI dash, okay. So we know that A is the vector and it can be represented as AI into EI, and that is actually equal to AJ into EJ dash. Yes, I was writing the cap here to indicate the unit vector, but just for the sake of simplicity I am omitting that cap, okay. But still these are nothing but the unit vectors in different coordinate system. This EI and EJ dash, they are nothing but the unit vectors in different coordinate system, okay. So now what we will be doing is, I can write AJ EJ dash, and now I can multiply with EQ, E dash, I mean EQ dash in both sides, okay. Now here I will ask you two questions. Can you recognize this one? Okay, so you can take some time, okay, to recognize this one. I mean, take some time, pause the video and take some time to correlate this one, that is this EJ dash into EQ dash, with any other special tensor that I have already talked about in the previous lecture, okay. You can pause the video and take a few minutes to just contemplate about this. Okay, so some of you may have come with an answer, but anyways, let us proceed. So this thing, right? So essentially, what is Ej dash? This is the unit vector, right? Unit vector for a particular coordinate system, right? True. So this j can take 3 values, that is 1, 2, 3. Now you tell me that if I do ei, okay, now I am writing this cap, okay, ei dot, I mean e1 dash dot e1 dash, what will be this? This will be 1, we know, right? Because this e1 dash is nothing but an unit vector having magnitude 1. And what will be this? This is 0. Okay, so that means if these subscripts are same, then it will be 1, and if these subscripts are not same, then it will be 0. Okay, so can I write this as, this whole story, can I write this as ei, or let me use this j and q, ej dash into eq, right? Here it was q. Okay, can I write this as delta jq? Okay, now you see this j and q, they both can take values from 1 to 3, but also we know that this is a special tensor, that is the Kronecker delta, and this is equal to 1 when j is equal to q, and this is equal to 0 when j is not equal to q. So we know this, right? And this is, I mean, what is the property of the dot products between different unit vectors? Only if this j is equal to q, then this e dot e equal to 1, but if this j is not equal to q, then it is 0. So I think that this expression is clear. If not clear, you have the full right to comment in the comment box, right? Okay, so I will now proceed through this step here. Okay, so then see, I can write here aj into delta jq, right? Aj into delta jq, and that will be equal to ai into ei into eq dash. So ai into ei into eq dash. Okay, now another thing, what will be now this expression? You see, if j is equal to q, then I can write delta jq is 1. So if j is equal to q, then I can write delta jq is equal to 1, right? Now if I put j equal to q here, then I cannot leave this j as it is. I have to put here also q. Okay, so therefore this is as good as aq. Okay, now this is equal to ai into ei into eq dash. Okay, so this was not okay, so I have made a little bit mistake, that is, this is a dash. Okay, I mean because this is a different component here from this one. Okay, this is a dash and this is also a dash. Okay, I am sorry for that. This is also a dash. this will be A dash and this will also be A dash. Okay, so then I have AQ equal to A dash I EI into EQ dash. Okay, is there something wrong? Just let me see. Okay, another thing, I have made a mistake here. I changed the sign, right? Don't worry, I will again go through the whole derivation so that you don't lose the track. Okay, here the dash will be here because I have written this side here and this side here. I have changed the sides. Okay, so therefore, I mean obviously because here I have the dashed unit vectors, so here also it will be dash and here it will be a dash, and here I will not be having any dash. Okay, so that is okay now. So let me go through the proof once again because I had made a small mistake here. So just to see quickly, that is, this is clear, these two are the same same expressions of the same vector in different coordinate systems, and I have written this side now here and this now here. Okay, now what I have done is I have multiplied by EQ dash into both sides. Now my question here, a very important question, is why I did not multiply by EI or EJ dash. Okay, so I could have multiplied by EJ dash or EI dash. So I am just putting my question here. Can I multiply by EJ dash instead of EQ dash? Okay, so this is your homework and you should comment this. Okay, you should give this answer in the comment box and I will be giving the answer in the next lecture. Okay, so this is the relation between AI and AQ dash. Okay, now you see that in both sides I have only one free index, that is Q, here and also here, and this I is a repeated index, so the rule is not valid, I mean the rule is not violated, sorry. Okay, and now this is actually written as AI into QIQ. Okay, so this QIQ is known as the transformation matrix. Okay, transformation matrix. So QIQ is equal to EI EQ dash. Okay, so transformation matrix, I should have written transformation matrix between the the normal coordinate system and the dashed coordinate system, and if I go back to this one, between this green coordinate system and the purple coordinate system. Okay, so transformation matrix is always defined for two specific coordinate systems. I mean, if you change the pair of coordinate systems, then this matrix will also be changed. Okay, okay, so this was for vector. Now if we have to do the same exercise for a tensor, that is, the components of the tensor will also be changed if we change the coordinate axis. Okay, So let us explore that situation. So firstly, if I have a tensor K, I will denote the tensor by 2 overbars. Okay. Now you see that second order tensor. So if it was a third order tensor, then I would have been denoted as k triple overbar. Okay, so the number of overbars will denote here the order of the tensor, right? So this is actually written as kij into ei, this one. So what is this? This is called the dyadic product, okay, of two vectors. So this is called the dyadic product. Now what is this thing? Okay, so what do you mean by normal dot product? Okay, so if I have two matrices, I mean two vectors, one is A and that is equal to A1 E1 cap plus A2 E2 cap plus A3 E3 cap, and I have another vector B that is equal to B1 E1 cap plus B2 E2 cap plus B3 E3 cap. If I have that, then A dot B is A1 B1, A2 B2 and A3 B3, right? So that will be a single scalar entity, right? So if I have to write that as a matrix quantity, that is A1 A2 A3 and B1 B2 B3, okay. So then is it correct? Let us just see. This is a matrix and it has the dimension of 1 cross 3 and it is 3 cross 1, so this is 1 cross 1, okay. So then it is correct, right, because this row multiplied by this column, okay. So this is called the dot product, and also this thing, I mean this thing is called inner product between A and B, okay. Now if I do the opposite thing, just the opposite thing, that is A1, okay, I write this one A1 A2 A3 like this, a column matrix multiplied by the row matrix B1 B2 B3, then what I will get? I will get here A1 B1, A1 B2, A1 B3, then A2 B1, A2 B2, A2 B3, right? Then A3 B1, A3 B2, A3 B3, okay. And you just see the dimensions of the matrices, that is, this is nothing but 3 cross 1, this is 1 cross 3 and this is 3 cross 3, so this is matched. Now this is another product between these two vectors A and B, and this is called outer product or the dyadic product, okay. So as this is A dot B, similarly this is A dyadic B, clear? So we need, I mean for vector we need three components of a basis vector to represent a vector. Similarly here Ei and Ej are the unit vectors, okay. So here I need 9 positions. So therefore, and see, these things are what? These things are basis vectors. Okay, basis vectors means what? Basis vector is like, uh, I mean, if you have done your linear algebra course sincerely, then obviously you will be you will be knowing this term basis vector. And if you don't know, so basis vector is like, if we have a vector space. Now again I am just coining some new terms, that is vector space. But if you have a vector space, for the time being you just think that the vector space is a space made of vectors. So this is not the authentic definition, but just for the analogy and just for the rough description. So in a vector space there are some basis vector in terms of which any other vector can be written. Okay, so it is like that, uh, those are the vectors, I mean those are the father or mother vectors. They know, I mean they can make any other vector. Okay, so basis vector uh, is the basis. So likewise these are the basis vectors. So when we are representing a vector, then only one basis vector is enough, that is 3 components of that vectors are enough if we are representing a 3-dimensional vector. But whenever we are representing a tensor, we need 9 components formed by those basis vectors. And if we need 9 components, then we have to go by this dyadic product. Okay, so this is not like a very authentic and formal description, but for the time being, just to give the analogy that why we are taking this dyadic product representation for the tensor representation. You can think of this analogy, that is, we need 9 components made by those basis vectors, and that is why to get 9 components from 3-dimensional vectors, we have to take their dyadic product. Okay, I hope this is clear, right? So after all this talking, now we are uh, comfortable with the fact that K can be written as Kij Ei cross Ej, not cross Ei, dyadic Ej. And in any other coordinate system, I have this as Kmn dash E dash m cross E dash n. Okay, so again, for the sake of simplicity and brevity in writing, I am omitting this cap sign. Okay, now I have to again do the same thing. Okay, that is, I have to find a correlation between this and this. Okay, so just let us write that thing. So objective is find relation between Kij and Kmn dash. Okay, so the step will be exactly same, that is the first step. So Kmn dash E dash m dyadic E dash n is equal to Kij Ei dyadic Ej. Okay, so multiply both sides by anything other than E dash m or E dash n. So also E dash I or E dash j. So anything other than E dash m, E dash n, E dash ei, sorry, E dash I or E dash j. So we cannot multiply by these four things, any of these four things, and I want to know that why we cannot multiply. Okay, this was the same question that I have put earlier for that vector case. Okay, so your job is to answer this question in the comment. Okay, so let us multiply by E dash q, and that is equal to Kij Ei dyadic Ej and multiplied by E dash q. Okay, now this thing is nothing but, I am just writing it, this is equal to Em into En I mean Em dash into En dash into Eq dash. Okay, so basically there is a property, that is A dyadic B, okay, into C is equal to A into B dot C. Okay, A into B dot C. So there is another very interesting fact. Okay, just let me tell it. I know that it can break the continuity of the derivation, but still let me tell it. It is very interesting. See, I will tell you a very interesting fact, that is, you see A dot B is a scalar, right? It is a scalar, not equal to a scalar, but it is a scalar. A cross V is a vector, right? A dyadic B is a second order tensor. Okay. Now you see vector is what? A first order tensor, right? First order. So this is what? Dot product. This is what? Cross product, and this is what? Dyadic product. Okay. So dot product is essentially decreasing the order of the tensor. Okay, that is, these are what? First order tensor, and these are converted into a zeroth order tensor, and these are what? First order tensor, and cross product is maintaining the order. Now dyadic product is increasing the order. Okay, these are first order tensor, but the result of the dyadic product is a second order tensor. Okay, now you see, that means this is a second order tensor, right? Second order, and this is what we are doing. We are taking a dot product with another vector. So a second order tensor is being dotted with another first order tensor. So ultimately this second order tensor will be reduced by order 1, and this is a vector. Okay, so there is no such dot product between a second order tensor and a vector. So it is just a multiplication, and it is analogous to a dot product. So therefore it is just reducing the order of the second order tensor to a vector. Okay, so, and you can verify this by a matrix. Okay, that is, if you take a second order matrix, that is 3 cross, so this is 3 cross 3 matrix. Okay, and taking dot product is taking the transpose, so 3 cross 3, and this will be 3 cross 1. So ultimately this will be a 3 cross 1, and that is a vector. Okay, 3 cross 1 thing. I mean, you can always check this thing by a matrix representation. Just always remember, that is, taking a dot product means, that is, you have to multiply this in a column vector form. Okay, like this. Sorry, not this one, like this. That is, I have multiplied this B as, I mean, if this is A, then it is what? B transpose, right? So A dot B means A into B transpose. So essentially, if this is a matrix Q, then I have to write Q into C transpose, and that will be equal to A into B C transpose. Okay. So these are the basics of linear algebra actually. Okay. So I would not like to remove this. Okay. So I mean, and from this fact only, this has come, that is, this dyadic this into this is equal to this into this dot this actually. Okay. A into B dot C. So this is equal to Kij, and similarly Ei into Ej Eq. Okay. Okay. Now you see that this is what. So just let me copy this line. Okay. Let me copy this and I will paste this here. Okay. So this we already know that this is delta NQ, this part, and this we already know that this is Q JQ, this part. Okay. Now again KML. Okay. Now this delta NQ is 1 when n is equal to Q. So if I put n is equal to Q, then this n I have to put is equal to Q. Okay. So I remove this n and I just put here Q. So it will be this one. Now this is Kij into QJQ into EI. Okay. Now this is equal to K. Again I have to eliminate this one. Again I will multiply by maybe E dash P into both sides. Okay. So QJQ into EI into E dash P, right? Now again I know that this E dash M into E dash P is equal to delta MP, and that is equal to K Ij, okay, QJQ into delta, sorry, and this is QIP, okay, this one, and this is delta MP. Now again this will be K dash into PQ, because this will be 1, this delta MP equal to 1 when M equal to P, and that means it is equal to Q. Now you can ask me that I could have written this P is equal to M. Okay. So then again if you write P is equal to M, and if you don't change this M here, then there is no benefit. Okay. So now your objective will be whenever you have any this is delta matrix Kronecker delta, you just seek for these this subscripts in any other term. So here I have this M common here, so I will just replace this M by this another alphabet P. Okay. I will take the advantage of the fact that delta MP is equal to 1 when M is equal to P, right? So then K dash PQ is equal to Kij QJQ QIP. Now we write this as Q Pi transpose Kij into Qjq. Okay, this is the formal writing, because we have to maintain this one, this I with this I, this j with this j. Ultimately you see that in the LHS this p and q are the free indices, and in the RHS we have this p and q are the free indices, because this I is being repeated, this j is also being repeated, so this I and j are not the free indices, these are the dummy indices. Okay, now this is the rule for transformation, I mean rule of transformation for the second order tensor, okay, between two different coordinate systems. Now let us try to find this relation between Kij in terms of K dash PQ. Okay, so then again we can write, we will start from the same thing, that is Kij, okay, Ei cross, I mean dyadic is equal to Kmn dash into Em dash dyadic En dash. Now I will be doing it a bit faster. Okay, so Ei dyadic Ej, and I will be multiplied by maybe Eq. So K dash Mn Em dash dyadic En dash multiplied by Eq. Okay, then I have Kij Ei into Ej into Eq, so that will be delta Jq, and this will be Kmn into Em dash into, okay, so I am just writing this one. Okay, then now here I have this delta Jq, so delta Jq I have here delta Jq, and I have here Kij, so this j and this j is common, so then I will write here Kiq, and what is the mathematics behind that? Delta Jq is equal to 1 when j equal to q, so I have to replace this j as well as this j also. Okay, so this will be into Ei is equal to K dash Mn Em dash, and this is Qn, not Nq, because you see that Qij is equal to Ei into Ej dash. Okay, I have defined the transformation matrix like that. Clear? Okay, so you see, I mean this actually is dependent on the definition of my transformation matrix. So if I had defined this, sorry, what, how this has come, this scale thing, I don't know. Okay, I don't need this scale, man. Okay, so let the scale be there. I don't need this scale. Where from this scale has come? Okay, if I cannot omit the scale, like if I cannot remove the scale, so let the scale be here. I don't need that. Okay, so now what I was talking about, that had I defined this one as delta Qi, okay, then all these definitions will be just interchanged. So then this could have been delta, I mean Qj, not Jq. Again I am repeating, had I defined this as Qi instead of Qiq, then all these definitions, so this would have been instead of QIP, QPI. Okay, so this thing is important. Okay, this notation is not so important, because this you can change according to your choice of, I mean, asserting this EI into EP dash. Okay, so according to that, I will write this as, okay, so EI into EJ dash is correct. Okay, this I don't require. Now again, QYQ, I will take the multiplication by EP. So this will be K dash Mn Em dash QQn into EP. Okay, again this is KIQ delta IP is equal to K dash Mn QQn into, now E dash M into EP, that is QPM, right? So then I have Q, now IQ into delta IP, so this I is common, so this will be KPQ is equal to KMN into QN and PM, and this I can write formally as QPM into KMN dash into QNQ transpose. Okay, so now just for the sake of understanding, here we had the relation between this KPQ and KIJ. So, and PQ was the index for the dashed coordinate system. So here also we will use the same. So I will just change the free indices. So here for the undashed coordinate system, we had Ij here as our index. See here, Ij in our undashed coordinate system Kij. So let us replace this P with I and Q with J. Now don't confuse yourself by saying that I mean, he has told that we cannot change the free index by any other alphabet. That is true, but if I have to change this P by I, then I have to change all the free indices in all the terms in that equation. Okay, so I will be writing the changed equation, that is Ij is equal to Q. So instead of this P also I have to write I, and this Q also I have to write J. Now Qi. Okay, now this M is a dummy index, right? This M is a dummy index as well as this N. So instead of this M I can write anything. Okay, so in our earlier derivation we have used PQ as our indexes, I mean indices in our dashed coordinate system. So let us use that only. So this will be Q. Okay, now Qi. Now instead of M I will be writing P, then it will be K dash P. Instead of N I will be writing Q, so it will be Q, and instead of Q in this equation I was writing J. Now this is okay. Okay, now I will write this equation and this equation side by side. So just let me copy it and I will be pasting here. Okay, so now what I will be doing is I will take this Kij and I will put this expression, this whole expression here. Okay, so let me put it. K dash PQ is equal to Q transpose PI. Okay, so QIP KPQ dash QQJ transpose QJQ. Okay, now you see that if this equation has to hold, then this and this must be identity matrices. Okay, because this and this are same matrices. So if this equation has to hold, this has to identity matrix and this also has to identity matrix. And since it is Q transpose into Q, This is also Q transpose into Q. So we have Q transpose into Q as our identity matrix. Okay. So see, for transpose what? A21 becomes A12, A31 becomes A13, A23 becomes A32, right? That is, the indices of the elements are being interchanged. That is why here also QPI, if Q transpose has the indices as QPI, then the original matrix has to have the indices QIP. That is, the indices has been interchanged. I think this is pretty intuitive, right? So that means this is a, sorry for the disturbance, my phone is ringing because of an alarm. Let me switch off that. Okay. Sorry for that. Okay. Now let me continue. So this is the property of an orthogonal matrix. Okay, orthogonal matrix. So our transformation matrix is essentially an orthogonal matrix. Okay, and we have to remember this property, that is Qij into Qji transpose is equal to delta Ij. Okay, because identity matrix is nothing but delta Ij. Or I can directly write as I. Okay, because it cannot be written as delta Ij, because here this I and j both are repeated in indices. Okay, but this we must have in our mind. Okay, let me make the box in a beautiful manner. Okay, अगर box नहीं तो यही सही. Okay, so let us proceed. Now the main thing comes. So I have my thermal conductivity tensor Kij. Okay, and for an isotropic material, Kij is equal to Kmn dash. That is, the elements in the original coordinate system and the changed coordinate system will be identical. So this will be true for an isotropic material. Okay. So now let us write this Kmn in terms of our Kij. So this will be Kim, Kjn, Kij. Okay, and this will be Kn, so Qmi transpose Kij into Qjn. Okay, with the growing experience, you guys will also be able to write this by your own. Okay, now see that now I am not directly deriving this, but I will be deriving this in in another way. So let us explore that. So I am claiming that, that for an isotropic material, Kij is given by B into delta Ij. Okay, that is B into identity matrix, and this is only a our claim, right? So let us verify it. So I will be putting this expression here, okay? So K dash Mn, this one is equal to QMI transpose into B delta Ij into Qjn, where this B is a constant, nothing but a constant, okay? So now you see that here I have this I common, so I will be changing this M by J, sorry, here I have this I common, so I will be changing this I by J, because this delta Ij is equal to 1 if I have I equal to J. Also I could have done this J common, I could have changed this by I. So let me do this one, because just for the change of flavor. So this will be Qin, okay? So now I am just writing this B separately as it is a constant. So it will be Q transpose Mi, okay? Now I can write this Qin as Qim into delta Mn, because you see that this thing here I have this M common. So if M is equal to I, then it is Qin. So this is equal to Qin. So this interplaying between this delta and these other matrices, and there is a very beautiful matrix that is a permutation matrix or permutation tensor, that is epsilon ijk. I have already introduced that. Now that is also a very interesting one, okay? Now in our tensor algebra we have, I mean, if you do a course on continuum mechanics, you need to be accustomed with this playing with these deltas and epsilons, okay? So now as we know that this is our identity matrix, so this is essentially delta B into delta Mn, okay? So that means you see that I proposed that my Kij is equal to B into delta Ij, and I got my K dash Mn is equal to B into delta Mn, okay? And you see that it does not matter that I write delta Ij or delta Mn, both are same, okay? So that means I am sure that Kij is equal to K dash Mn. Now it is proved that only for an isotropic material I can write this K as B into delta Ij, that, and where this B is a constant, right? So now this is done. So now if you put this into your thermal energy balance equation, then you get the form that you are accustomed with, and I mean that is by dealing K as a constant, okay? So now almost the basic theory is completed, and in the, I mean from the next lecture we will be starting with our special cases of conduction, okay? That is the steady state, the unsteady state, the one-dimensional conduction, the two-dimensional conduction. We will be exploring that, a semi-infinite domain, okay? So everything we will be doing from the next lecture, okay? So until that, if you have any doubt, you can always post that into the comment box. And also if you think that my teaching is not up to the mark, I mean if anything is lacking, you can also suggest me that into the comment box. Anything, that is, if you are having any doubt into your mind, or if you want anything that this would be better if you do it like that, okay? So so we will be meeting in the next lecture. Until that, goodbye, take care, and thank you.